Hi, I am Marco Panizza. I'm the European Application Manager for Vicor. Defense applications pose the most demanding requirements for engineers. So today I'm going to explain you how engineers can develop systems meeting the most stringent transient specifications for use in military vehicles. Military electronics equipment must meet a wide range of requirements. First and foremost, the product must be rugged and able to withstand the shock and vibration that it's likely to encounter during use. With the increasing use of electronics to gain a strategic advantage, space is at a premium, requiring small and compact power supplies. Military vehicles are used in very different environments, from freezing conditions to hot deserts, so wide operating temperature ranges are very important. Efficient cooling, such as the base plate on bricks, can help extend the system's operating temperature range. Electrical requirements are defined by the standards in great detail. In addition to strict EMI limits, power supplies must be able to deal with transients generated by the imperfect power sources found in military environments. Let's look specifically at transient immunity, which is defined by specifications such as MIL Standard 1275 in USA and DEF Stan 61-5 in UK. These define the worst-case spike and surge conditions. Spikes are characterized by a high voltage rise, short duration, and low energy. Surges, on the other hand, have lower voltage rise with a long duration and a high energy. In this table, we can see the similarity between the two specifications. Although off-the-shelf products such as Vicor's MFIAM range are available to provide transient immunity, they are unable to meet the requirements of the most demanding military specifications. Spikes can be eliminated by using a parallel device such as a transort. Long-duration surges need a serious transient protection circuit which drops the excessive voltage during the surge event. Ideally, such a device should allow nominal current to flow and guarantee normal operation during the surge. For high-power systems, power handling capability can become demanding because the surge protection device must drop the excessive energy. A Vicor module rated 28 volt has a maximum input voltage of 36 volt. As we have seen, the input transient can reach up 100 volt. 64 volt must be dropped across the surge protection device. The best device for this application is a MOSFET. A BJT could also be used, however the 0.5 to 1 volt voltage drop during normal operation might not be acceptable because of the power losses that it introduces. Let's have a look at a typical circuit to protect against transients and surges. The capacitor across the input acts as the main device to absorb short-duration, low-energy spikes, with a transort providing added protection. All of the remaining circuitry addresses the problem of high-energy surges. It does this in two ways: by clamping the output at 35 volt if the input voltage rises beyond these, and by using the PC pin to shut down the converter if the overvoltage condition persists for more than 55 milliseconds. A charge pump provides full enhancement gate bias to the MOSFET Q1 during normal operation. This is accomplished by U1, an ICM 7555 timer, which generates a rectangular waveform at 109 kHz that is peak detected and level shifted by R3, C4, D1, and D3. Capacitor C7 limits the rate of rise of the voltage across the output to 160-170 volt milliseconds, which in turn limits the inrush current at startup to 3.5 amp with a 1000 microfarad capacitor across the output. The output voltage is compared with the LM10's reference voltage. If the output of the circuits exceed 35.3 volt, the error signal at the output of the LM10 is used to control transistor Q2, causing FET Q1 to act as a series pass linear voltage regulator. The power handling capability of this circuit is limited by the FET Q1, as it must dissipate the excess input voltage. It is therefore important to consider the choice of component carefully. For higher power applications, it might be necessary to use several MOSFETs in parallel, in which case care must be taken to select MOSFETs that will share current equally. You can check out the application note on the vicorpower.com website that provides more information. Shutting down the DC-DC converter will protect the MOSFET in the case of sustained overvoltage. If a surge lasts longer than about 50-60 milliseconds or repeats faster than once per second, Q3 will turn on, turning off the attached module. With the module off, the MOSFET no longer needs to supply a load, and therefore the circuit can withstand 100-volt surges almost indefinitely. There is a lot more information at vicorpower.com. In addition to product data, you can access our extensive technical library and get information on designing high reliability and safety critical systems. And you can improve your knowledge of power supply designs by taking our tutorial videos. In alternative, you can send an email to videos@vicorpower.com and I will be glad to help you out answering all the questions should you have. Thank you for watching and don't forget to check out our other videos.